Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 5.4.7, a brief look at the Riemann zeta function. Now, the Riemann zeta function, we're not going to talk about the analytic part of it, just kind of the counting part of it, really. Because really it's a function that intakes a complex number and outputs a complex number. But we're going to be concentrating on the on how it's useful for counting purposes, especially looking at the coefficients. So, for instance, let's just kind of look at another way of thinking about this Riemann zeta function for a minute. What if we thought about a geometric sum formula for like 1 over 1 minus this? Now, if you've seen a geometric sum, an infinite series, there's a nice formula if you have like something in your and you're adding like different powers of it going up, it'd be like 1 over, and if the first term is a 1, the first term goes here, and 1 minus, well, you're multiplying by every time. Here, multiplying by 1 over p to the s to get from term to term. So really, this is like a geometric series, and you can write it like this. And this symbol just means product. It's the product of all these guys. So now, what about this right here? Let's see how this is related to this formula right here. Now, these k's, these are all the counting natural numbers or positive integers, starting at 1 and going up. These are p is a prime number. Now, if you think about multiplication distributing, there's going to be a unique way that, gets p squared with something else, with another, with a different prime, because we're taking this and we're multiplying it to the same thing with a different prime and a different prime and all the primes. And the different terms that we get out of this will actually be in one-to-one correspondence with all of the counting numbers, as long as we just take products where most of the time we take a 1 from most of the factors, so we can multiply an infinite number of 1s and just a few of these other guys, and we end up getting all the counting numbers. We'll just say that if we ever if that is not the case, if we have an infinite number of these guys in the multiples and not simply just the ones, then that term will just say it's 0, or we'll just ignore it, or kind of mod out by those guys, say, in some sense. So doing that, and you can also kind of think about that analytically as well, but which means use a calculus convergence sense, which we won't, but we'll just kind of say modding out by them. So right here, this becomes, so that's interesting because this is another description of the Riemann zeta function right here, which is in series notation. Okay. Now here, here we used a k, but here we're using n, but it really means the same thing. Okay. So that's interesting, because what if we take the inverse, the multiplicative inverse of the output of the Riemann zeta function, so 1 over it, we can think of it as the product of all these guys with a -1, which is the product of all these guys with that, which is interesting for us, because this is, remember the counting function that we had, the Mobius arithmetic counting function, this mu guy, mu of n, it actually is the coefficient of n to the s in the reciprocal of the Riemann zeta function, which allows us to think of multiplication by a Riemann zeta function or reciprocal or whatever, allows us to do a lot of counting with it, because we see this Mobius function, which has a lot to do with counting, as a coefficient of this n to the s. Now notice, we're not looking at like powers of like x to the n. Instead, we're looking at powers of like n to something. Or we're not even looking at powers of that. We're just looking at n to something. So we kind of replaced this. Instead of like x to the n, it's like n to the x, where s is, you can think of it as x. So it's kind of replacing what, so this is kind of a funny type of series, not a power series. It's called a Dirichlet series, if you want to be technical. But the coefficients of it and how it works are great for multiplicative type problems, ones that deal with factorization type posets and things. And so it has a lot to do with factoring. And the coefficients of it happen to be that nice Mobius function that we saw earlier. And you can actually get this by looking at this a little bit in some sense. Because let's think. If we, so this is a product of a lot of these guys with lots of primes. Now, notice in here, there's only, you'll never see a power of P that's more than P to the S. You won't ever see any P to the 2 S's or anything, because this is all you get from P, which means it's like you're ignoring or zeroing out anything with a square factor. Now, if you have two primes occurring, that'll be like a negative in distributing, will be like a negative and a negative together. So it'd be positive 1. And 3 be negative, negative, negative would be negative 1. And really, we end up getting the same definition that we had for the Mobius counting function. So it's kind of a neat idea that the reciprocal here has that. Can it really be used? It can. There's an exercise in the section that looks at that, but for us, we'll be done looking at that for now. Thanks for watching.